Okay, we shall begin. So Monday, I introduced kind of the concept behind the Gibbs sampler, in that we have a high dimensional probability distribution, and we want to generate samples from this high dimensional distribution using a kind of a naive Markov chain, like the Metropolis algorithm or Metropolis-Hastings algorithm requires you to propose a new location in like a new value that exists in this high dimensional setting. And the problem with that is that it might take a while before you get a decent proposal that you might accept, okay? Because if you have, say 20 dimensions, okay, you need to propose 20 reasonable values. And even if you propose, say, 19 reasonable values, if one of those values, if the 20th value is unreasonable, okay, then the probability of you accepting that the entire coordinate is going to be low. And so the Gibbs sampler says, you know what, let's just propose one value at a time. Let's have a unidimensional problem. But that requires us to factor the entire problem, okay, down into a bunch of univariate probabilities, okay? And that itself could be a little bit challenging. So I'll post your final homework assignment, and I'm going to ask you to do that in your final homework assignment. And I've posted a document. This talks about, if you have a multivariate normal distribution and you condition on one of the values, what does the univariate probability distribution look like? So this document's from a textbook, and this will kind of cover that information. And so you'll have to, do some reading and a little bit of kind of going through this in your homework. But anyway, I wanted to talk about kind of a certain class of models, okay, called hierarchical models. And these naturally set themselves up well for being able to be factored into conditional distributions, okay? I put a lot in this slide deck, so maybe we might not get through the entire slide deck. That's okay. We'll continue on Friday, okay? All right, so this is just a review of the Gibbs sampler, all right? And it says that there is a target multivariate probability distribution, okay, probability density, and our values x exist in d dimensions. So this could be 20 dimensions, 2 dimensions, 100 dimensions, okay? And because it's a Markov chain, we're going to be generating a sequence of these values. So we're going to say x at time t is going to be x1 at time t, x2 at time t, x3 at time t, all the way up to xd at time t. So this is just kind of our notation. And what we want to do is we want to produce another value, the next value in our Markov chain. So that will be x at time t plus 1, which will be x1 at time t plus 1, x2 at time t plus 1, so on and so forth, up to xd at time t plus 1. And in order to get this thing, rather than just proposing an entire new coordinate in this d-dimensional setting, we're going to propose one coordinate at a time, or actually not even propose. We're going to just generate one value at a time, okay? And so I wrote, factoring a joint distribution into univariate conditional distributions could be difficult, but if you are able to do it, then you just, you have the probability function, okay, your PDF, for x1 based on all of the other coordinates, so holding everything else kind of constant at x at time t, x2 at time t, up through xd at time t. You have the probability distribution of x1, and you generate one value, okay? And then once you have that one value, you use that, okay? So this is your latest value of x1, the x1 coordinate. You use all of the other values. Oh, this should say x3, okay? x3, not x2, okay? And then you'll generate your x2. And then once you do that, you'll generate x3. You use the x1, the latest values of x1 and x2. You don't have an x3, but you have x4 and so on and so forth. And so whenever you're going to get the ith value, you get, from 1 through I minus 1, and then I plus 1 up to d, and so on and so forth until you get to your last value. And so you generate values from each kind of probability distribution, one coordinate at a time. And that's the Gibbs sampler. So the Gibbs sampler works very well for a class of models called hierarchical models. Hierarchical models are set up using conditional distributions, and so because the hierarchical model lends itself to or is set up using a conditional distribution, trying to derive these conditional distributions is not necessary. It's already part of the model design, okay? So what we're going to do is we're going to go back to this beta binomial baseball example, okay? And if you remember that example, we said each baseball player has some random value variable theta, okay, which is their batting average, okay? And that, based on that batting average, they produce a sequence of kind of hits and outs, and we had to do some Bayesian inference to say, okay, if this is the sequence of hits and outs, what do we believe their batting average to be? And we said their batting average, rather than using maximum likelihood estimation, where we said, if they got 5 hits out of 10 at bats, their maximum likelihood estimate would be 50% batting average, 0.5. And we say, well, that doesn't make sense because in baseball, it's rare for a player to have a batting average of over, say, 0.32 or something like that, 0.320. 0.3 would be really good, 0.2 is bad. Most players' batting average is somewhere between those two values, and so we had we used the Bayesian model here. We had this prior distribution where we had shaped parameters 81 and 219, which, when you go from 0 to 1, it produced kind of a peak like this, where most of our values were, say, between 0.2 and this is not to scale, but 0.2 to 0.3 was kind of this is our prior distribution for theta. Okay. So this is kind of what we said, and we said, all right, this is going to generate some value theta, okay? From here we get a value theta, and then using that goes into binomial with parameters n and theta. And we plug that theta in, and then this is going to generate your sequence of hit, out, hit, or 1, 0, 0, 1, etc., etc. Okay. That's your observed data. So the issue here is, how do we get these numbers 81 and 219? Okay, we just kind of we said, well, this is kind of my understanding of baseball, and I said, in the history of baseball, the greatest batting average, highest career batting average of all time was like 0.35 or something like that. I don't remember, 0.362 Ty Cobb or something. Okay, and then just in general, there's kind of, a professional batter is expected to have a batting average of at least 0.2, otherwise they might get cut from the team, okay? So, but what if we don't want to just arbitrarily pick these numbers, 81 and 219, okay? This is where we have a hierarchical model, okay? Rather than just me coming in and saying the numbers I'm going to use are 81 and 219, we're going to treat this as a random variable, okay? We're going to call this thing alpha, and we're going to treat this as a random variable beta, okay? So instead, we have some mystery distribution here, and from here we're going to get a value alpha. We have another distribution here, and from here we're going to get beta. And rather than me plugging in 81 and 219. Okay, so we're going to treat those values as random variables themselves. So it's kind of, there's, again, a hierarchy of random values, okay? So alpha is a random variable with its own random distribution. Beta is its own random variable with its own kind of probability distribution. And so these things, because these are, so this is the parameter. So here's our observed data. The data comes from some distribution with some parameter, right? This is the parameter that we are trying to figure out. Okay, and this is kind of our unknown parameter. We try to do Bayesian data analysis, okay? Or you could do maximum likelihood estimation to get your unknown parameter, okay? These are now also unknown parameters, but these parameters generate this parameter. So these things are known as hyperparameters because they're kind of a level above, okay? So these are also parameters and they are known as hyperparameters. Also parameters called. Okay, so those are also parameters and they are called hyperparameters. Okay, so the distributions that produce the hyperparameters, okay, these, I guess, so you have a prior distribution that produces the parameter, right? You also have kind of prior distributions that produce your hyperparameters. These are known as hyperpriors, okay? It's so the random distribution that produces alpha and beta, these are known as hyperprior distributions, okay? And they produce our hyperparameters. The hyperparameters define our prior distribution, and from our prior distribution we generate our unknown parameter. Our unknown parameter goes into our probability distribution like the binomial, and that generates our observed data. Okay, so we're taking one layer out. Okay, so I don't know if that's okay regarding this hierarchy. It feels a little bit silly. And then it can keep going forever, right? Technically, right? It's like turtles all the way down. Somebody could say, well, how do you pick your hyperprior distribution? You know, those also have parameters. Okay, the parameters that define this would be your hyper parameters with its own and if you wanted to, you could have a own hyper prior distribution, and that itself could also, at some point you got to say, all right, that's enough. Okay, we'll stop here. But I mean, technically, it could go on for forever, right? So the hyperpriors can also have its own parameters. These are called hyperparameters. I'm not joking. All right, and we just basically, at some point, you just say, all right, we're going to just pick these values ourselves. Otherwise, they could technically go on for infinity. So we usually stop after a certain level here. Okay, so we want to say, well, what kind of random distribution makes sense for generating our values alpha and beta? Okay, what kind of values would make sense for generating these values 81 and 219? So you got to do a little bit of thinking here, because we want whatever hyper prior distribution we have, we want it to be able to generate what we thought were reasonable numbers, right? When I had to pick these numbers myself, I picked 81 and 219, and I said, I think that's kind of a reasonable number, and we want our hyper prior distributions to produce, these seemingly reasonable values here. Okay, hang on a second. Okay, and these numbers, 81 and 219, one way to kind of think about it is you could think of these as kind of like pseudo counts. So if you remember, the way the beta binomial distribution worked was, when you saw an additional 10 at-bats and 5 of them were hits or something, you don't just go 50% 5 out of 10, but you added 5 to the 81. You got 5 hits and 5 outs. So your updated parameters at the end were 81 plus 5, 219 plus 5, and it was like 86, 224. Okay, and you basically just kind of add your number of yeses and nos to these shape parameters, alpha and beta. Okay. And this idea of 81, 219 was that for a generic professional baseball player, before you actually saw them perform, your assumption is kind of like, this is a player who, out of a total of maybe 300 at-bats, had 81 hits. Okay? So they had 81 hits, 219 outs, and these are kind of like our imaginary counts of hits and outs. And then using that as kind of a starting point, we'll then add the actual observed data that we see. Okay. And so if you do that, we could calculate values like the omega, the mode, right? And the mode of this 81 is basically alpha minus 1, and then alpha plus beta minus 2. And so it gives us a peak just under 0.27. The mean is 0.27, but the mode is just a tiny bit lower, 0.2685. Okay, and that seems kind of reasonable for a batting average. And another way for us to think about this is we could say, well, what if rather than using 81 and 219 directly, we could say, let's pretend I saw 300 at-bats and I want the peak to be, around 27% or 0.2685. And you can kind of backwards derive these values. So you could present it as 81 and 219, or you could have kind of the total number of pseudo observations and then the, quote, the batting average of those pseudo observations there. Okay. So this is just another way to express. So you can say, I'm going to use shape parameters 81, 219. I saw 81 hits and 219 outs. Or you could say, I saw a total of 300 hits, and I want the peak batting average to be, 0.2685. Okay, and if you express it that way, you can kind of back derive your values A and B. Okay, and so just to kind of this is going to simplify our work a little bit. Okay, we're going to just choose for our model. I'm going to just keep K arbitrarily selected at 300, and then we're going to just use omega as a random value from a hyperprior distribution. Okay, so I'm kind of So we're going to just kind of keep k set to be 300. Right, so we're going to keep k equal to 300, and then we're going to keep we're going to set omega equal to some unknown value, and if omega is like 0.27, that will correspond to 81,219. If omega is say 0.3, then that would become something around 90 and 210. If omega was say 0.2, that would be closer to like 60 and 240 or something like that. Okay, so we'll just arbitrarily say k, keep k, and then we'll change our omega. So we just have one random value, and by changing the omega one random value, it will correspond to kind of like what alpha and beta are going to be. Okay, so it's basically just omega times k and 1 minus omega times k, but just to kind of get it a little bit, you know, we have this plus 1, minus 2, etc. Okay. So that's what we'll do, okay? And so omega is going to come from a beta distribution, okay? Remember, beta is always go between 0 and 1. And we're going to say omega comes from somewhere, and we want it to be probably something around 30% itself, okay? So this beta distribution that's going to generate omega, okay, and then the omega will kind of multiply by 300 to get what my alpha and beta are going to be. Okay. So here again, you have your parameters. The theta comes from a beta distribution with hyperparameters 81, 2, or alpha and beta, and alpha and beta are determined by this omega, which is going to be its own hyper prior distribution with its own hyperparameters, okay, or hyperparameters, okay. And so we have to kind of pick some arbitrary values. And again, I'm just going to pick some arbitrary values. This will be A omega and B omega to designate this beta distribution. Okay. So all of these things, this is kind of our hierarchical model. We have k equal to 300. This is arbitrarily selected. I'm going to have omega coming from a beta distribution. These values, A and B, A omega and B omega, are arbitrarily selected. So at some point, you do have to arbitrarily select some values. But every time when, you know, as you kind of insert a layer between your arbitrary selection and the actual data, you allow for a little bit more data flexibility, okay, or allow for a little bit more flexibility in the model. So when we did the beta binomial example, you know, at the beginning of the course, we arbitrarily selected 81 and 219, okay? And so that kind of limited the kind of values that we could see. Right? So here we're basically just inserting another level of kind of random Bayesian probability stuff between our arbitrary selection. Okay, so it's just kind of I don't know, giving people a little bit more freedom. Okay, so rather than making the rules and then saying, okay, let's see what happens, we're going to say, all right, I'm going to make these rules, then we'll let some random process happen, and then after that random process, we're going to let another random process happen. We're just kind of inserting additional layers of randomness between our arbitrary decisions. At some point, you do have to make arbitrary decisions, though. All right, so we have this. Omega is used to decide our alpha and our beta parameters that go into our prior distribution. And then once we have our prior distribution, that's used to generate our theta, okay? And then once we have theta, we plug that into basically our Bernoulli or our binomial thing, and that generates our observed data X. All right, so this is kind of our diagram, Okay, we have, this is our hyperprior. That generates omega. Omega is used to determine our hyperparameters, which determine our prior distribution. The prior distribution generates a theta, and the theta goes into our Bernoulli or binomial process to generate our observed values y. This is our hierarchical diagram. All right, let me give you some view quiz answers. Oh, shoot. Okay. Oh, maybe I messed this up. All right, your first two answers are A and B. A and B are your first two view quiz answers for today. Okay, so now that we have this kind of hierarchical diagram, we can, I don't know why this thing is popping up. Okay. We can use this hierarchical model to explain the data from, say, multiple players. Okay, so rather than just seeing one player sequence of hits and outs, we could have a bunch of hits and outs, okay, for a bunch of players. We're going to assume each player has their own batting average, theta 1. Player 2 has batting average theta 2. Player S has batting average theta S, okay? And, you know, each of their things go and generate their sequence of hits and outs, okay? And the thetas, you know, come from that prior distribution, and then the prior distribution is generated from our kind of our hyperprior, right? So this is it's the same model as this, except now we're going to use it to model data from multiple players, okay? So you still have this hyperprior distribution to generate your hyperparameters, alpha and beta. And then once you have that, you have a slightly different beta distribution, okay? Or I'm sorry, you have a beta distribution, but each player, they're going to get a different theta value here, okay? So player 1's batting average will be come from this beta distribution. Player 2's batting average is also going to be randomly sampled from this thing, okay? And then using that, you will get a different sequence of hits and outs, okay? Maybe another illustration here, okay? Let's say we have these wheels, okay? And then in these wheels, part of it is shaded to be basically a 1, and part of it is shaded to be 0, okay? And so we have this wheel-making factory, right? And they kind of make all of these things, except the wheel-making factory, I don't know, the machine isn't super accurate and consistent, so sometimes the wheel-making factory, the amount that's 1 and 0 is small, and sometimes the amount that's 1 and 0 is bigger, okay? So we have this factory that makes these different wheels, okay? Now, depending on which wheel you select, that's going to generate your sequences of 1s and 0s. This one's probably going to be more 0s than 1s, okay? Whereas this one, okay, well, all of them, but this one, because it's smaller, you're going to have less, and then this one, you know, might have something closer to 50%, right? So the sequence of 0s and 1s that you get from each of these wheels will be different, right? And that's basically what we have here. This is player 1's kind of wheel. This is player 2's kind of wheel, player sub S will be kind of like what their wheel looks like. Okay, these wheels themselves, comes from some random process that will determine, how much is basically a 1 and a 0, and that's what we have. And so we said, okay, overall, if we looked at all of the wheels that this machine is making with the different kind of shaded areas of 0s and 1s, what's kind of like its overall distribution there, okay? So same idea here, okay, of having this, we have the data for each player, okay? So there's it's conditioned on each player's own theta. So we have a theta sub S, okay? That theta sub S comes from a beta distribution, all right? And so all of the different theta S's come from this beta distribution. This beta distribution has its own parameters, hyperparameters of alpha and beta, which are determined from this omega. And the omega itself comes from a top level distribution here, okay? So this is, these diagrams come from the textbook Doing Bayesian Data Analysis, which I've linked in our syllabus. It's the book with the puppies on the cover, okay? And so we have these different values theta. Each individual player generates their own kind of sequence of 0s and 1s, okay? Here's another kind of diagram, all right? So we have our hyperprior distribution. This is a beta distribution. From that beta distribution, we draw some value omega, some random value omega. And we use that value omega to get our A and B, okay? Because we said we're going to just arbitrarily set k equal to 300. And so that's going to give us our alpha and our beta. That goes into our beta prior distribution. From our beta distribution, we generate a random value theta 1 for player 1. That theta 1 goes into a Bernoulli or binomial, and we get a sequence of 0s and 1s, okay? From this beta distribution, we get a different value theta 2 for player 2. They get a different sequence of 0s and 1s. We have a theta 3, and then we get another sequence of 0s and 1s, and so on and so forth. Okay, so player theta S looks like this. Okay, so this is kind of the diagram explaining the different sequence of 0s and 1s of hits and outs that we get for each kind of player, and we're trying to figure out this prior distribution and whatnot. Sometimes you will also see these kinds of diagrams represented with plates. Okay, this is the plate distribution or plate representation, and in the plate representation, you just have the parameters. Okay, and you don't have these things that say like, okay, this goes into I guess the distribution itself just gets kind of written next to the parameters. So here we say alpha and beta, okay, come from go into a beta distribution, right? These things, and then and that generates a value theta sub S, which will generate our values here. Okay, this plate here represents the plate with an S in the corner. Okay, represents that this is kind of repeated across the different players that we have. Player 1, player 2, player S, so on and so forth. So it's kind of, because this part is duplicated across the different S players, we just kind of put it on a plate, and we say, all right, player 1 is going to have his own theta S, okay, with his own kind of sequence of YIs. Player 2 will have their own theta S with their own sequence of YIs. Player 3, so on and so forth. So this is also similar. This is another way of expressing this kind of concept. And so a lot of times, but if you do read some like Bayesian statistics papers and stuff, you might see a plate diagram drawn something like this. Okay, so we're going to say we have some big matrix of data of kind of all of the hits and outs of, say, 10 different players, all right? And we have the actual value, y sub si, random variable y si, is whether the player got a hit or an out, a 0 or a 1 for player S. And based on kind of all our big matrix of data, we want to estimate all of the unknown parameters. Okay, so we have 11 values. Okay, we have each of the players' thetas. Okay, we have the theta for player 1, player 2, so on and so forth. Okay, and then there's also an omega, okay, which was used to generate our alpha and our beta. Okay, so that's kind of our prior hyperparameter. So we have our unknown parameters theta, and then we have one hyperparameter, omega, okay? And then the other ones, these other values, k, alpha, k, a omega, and b omega, these are arbitrarily selected, okay? So again, at some point you do have to make arbitrary selections, but we have this one kind of additional layer of randomness to kind of remove, distance ourselves, our arbitrary decisions from the data, okay? Versus, in week 1 or week 2, we said, I'm going to pick 81 and 219 as my hyperparameters 80 for the prior distribution, okay? Okay, so this is this slide is scarier than it actually is. Okay, if you think about how do you explain all of the data, the joint distribution of everything, it's kind of there's a whole bunch of parameters, right? We have 11 parameters, so our data exists in 11-dimensional space, okay? And the posterior distribution of everything joint together is we got theta 1, the joint distribution of theta 1, theta 2, up to theta 10, and our hyperparameter omega, okay? And then given the data that we have, and then our arbitrarily chosen values, the hyper, is this a hyper? The A omega B. So these are arbitrarily chosen, and then our data, observed data Y. Let me slide this thing out of the way, okay? And so if you wanted to do Bayesian analysis here, you change it to, okay, what is the, so this is our posterior, this is our likelihood times our prior divided by our marginal, okay? So the likelihood is, what is the likelihood of the data given all of our unknown parameters that we're trying to figure out, okay? And then we also have the prior distribution of all of these parameters, okay? And then we have we're not used to seeing a given value in our priors, but these things were still arbitrarily selected. So we do have to kind of say given our arbitrarily selected values of A, B, and K, okay? Divided by our marginal. Now this is just a constant, so we can get rid of it and just say it's proportional to this, okay? And then, okay, and so now we have the likelihood of Y given all of this times our prior distribution of all of this, okay, given A, B, and K. And then if you multiply these two things together, this is just the joint distribution of Y and all of our data. Of all of our data Y and all of our prior parameters, okay? So this is the joint distribution given our arbitrary choices. And what we're going to do is we are going to factor this into a bunch of conditional distributions, okay? And so this is where the Gibbs sampler, that way we can use the Gibbs sampler, okay? So this last row here is just the joint distribution of everything. And if you think about the nature of the data, if you capital Y is a big matrix, right? And we got, hits and outs and this is like player 1, player 2, player 3, so on and so forth. But really, it's just, if you think about the sequence of player 1's hits and outs, it just depends on that own player's own theta value, okay? Player 2 only depends on their own theta 2, okay? So we're going to factor this, the joint distribution of all of our values to P of y1 given theta 1, P of y2 given theta 2, all the way up to player 10's mystery theta value given, player 10's observations given their mystery value. And then we have the theta 1, player 1's mystery value comes from this prior distribution with the parameters alpha and beta, which can be determined by omega and k, okay? And so we have that for all 10 players. We have to figure out, okay, what is the distribution there? And then we have to figure out, okay, what value of W did we get if we have a hyper prior, okay? Or a hyper prior distribution with parameters A, omega, and B omega. This is a lot. I hope it's okay. All right. So this is what we have. I'm just rearranging terms, okay? And then I'm just replacing omega and k into kind of our slightly more familiar alpha and beta. Because if you have omega and k, you can get alpha and beta just as easily, okay? So we're going to say this entire joint distribution, whatever it is, can be expressed as a product of basically the likelihood of getting your ones and zeros given some unknown parameter theta, and then the beta, this is a beta distribution. What is the likelihood of getting theta with hyperparameters alpha and beta, okay? And you do this for player 2, given their unknown value, and what's the probability of getting that, whatever value you got with alpha and beta. And you do that for all 10 players. And then we still have one more, okay, what is the distribution? This is kind of our prior distribution for omega, given the our arbitrary choices of A and B, right? All right, I guess we'll probably get through one more slide for today. Then we'll continue this on Friday. Okay, so if we look at this last line here, we factored the joint distribution of everything into the distributions of basically each row in our Y matrix, okay, times the distribution, basically our distribution of getting that individual batting average, right, for all 10 players. And then finally, we multiply that by the distribution of omega itself, okay? So again, keep in mind, each row is the result of random draws from the Bernoulli that depends on only that specific player's batting average. Each player's specific batting average theta s is the result of a random draw from the beta distribution that depends on our shape parameters alpha and beta, which are determined by our values omega and k. And then omega is the result of a random draw from a beta distribution with these values A, B, and K, and those were arbitrarily determined or selected hyper parameters. And so we are going to set this up to use a Gibbs sampler that will take advantage of this kind of product of all of these conditional distributions. Okay, so yeah. Okay, so we'll pause here, and then we'll continue on. And we'll talk about, okay, how do we draw from all of these things, okay? So eventually, this is what we want to do on Fridays. We're going to start generating these values. So we have our observed values y. So it's kind of, so you want to be able to explain your observed values y. Okay, this is no longer, there's no random here, right? And then we also have our arbitrarily selected values of like K and A and B. So you kind of have like two anchors. You have one anchor, which is the observed data, and you have another anchor where you have arbitrarily selected K, A, and B, okay? And then you have kind of this random process, and we use kind of the Bayesian inference to figure out, okay, what are the values of theta and what are the values of alpha and beta, or in our case omega, that determine our alpha and beta, that can then be explained, that can then be used to explain the data. So at one end we have the data that's observed, that serves as kind of an anchor, and then on the other end we have our arbitrary choices, and then we allow the Bayesian inference process to figure out, kind of distributions for each of these unknown values here. Okay, so that's what we'll do, and we'll take a look at that on Friday. All right, let me go ahead and give you your final view quiz answer.